So, dear students, we'll proceed further in the same section of vibration measuring instrument. So far, we have obtained this ratio Z by Y, and if you plot this ratio with respect to the frequency ratio, we'll have a plot like this. Mm, Let's say we'll start from here as 0, 1, 2, 3, and 4. This coordinate gives us the ratio of z by y. Okay. Then we'll have 1, 2, 3, and 4. So let us redraw it up to this point. Okay. Now if you plot uh, this horizontal coordinate is for omega by omega n, right? So now if you plot the variation of z by y with respect to omega by omega n for different values of zeta, okay, we'll have graphs like this. So these are the plots for different value of zeta. And this first one, zeta 0, the second one for zeta equal to 0.1. Okay, this one is for zeta is equal to 0.2. This one is for zeta is equal to 0.3. Okay. This one for zeta equal to 0.4. Okay. This one for zeta equal to 0.5. This dotted curve is for zeta value of 0.707. Okay. And the last one, zeta is for 1. Okay. So from 0 to 1, 0 to 1 indicates the range for acceleration, range for acceleration, and this range from 3 to 4 indicates the range for vibrometer. Vibrometer. this way we can plot the response. Now, coming to vibrometer, displacement measuring instrument. Okay, displacement measuring instrument is also known as vibrometer. Now, you can write it is an instrument used to measure the displacement of a vibrating system. Okay. If the natural frequency if the natural frequency of the instrument is low when compared when compared to that of the mm, vibration to be measured, that is, we can say omega by omega n greater than 1, then the ratio z by y approaches unity value for all values of zeta. Okay, as we have already seen in the figure. So we can say omega by omega square divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square whole root over is greater than is almost equal to 1. Let's say this is equation 11 from the preceding derivation. Then we have z is equal to capital Y sine omega t minus 5. This we have already taken. Let's say this is equation 12. Under such circumstances, you can write such circumstances, the relative motion of mass of measuring unit, you can say, of measuring unit is equal to the displacement to be measured. To be measured. Okay. We can say the excitation displacement of base. Okay. However, however, since z by y equal to 1, or we can say z is equal to y, the range of amplitude measurement is constrained by the size of the instrument, such an instrument is called vibrometer. Vibrometer or sissometer. Further, we can write when omega by omega n is, we can say, greater than or a comparatively larger value than 1, it can only be possible, only if the value of natural frequency omega n is root over of k by m is low. Okay. When denominator will be quite low, then only this value will be possible. That is, you can say the spring stiffness should be low, should be low, and mass should be large. Should be large. This generally results a bulky instrument which is not desirable, in many instruments. In many instruments, okay. And hence vibrometers are not usually preferred not usually preferred for vibration measurement. Vibration measurement. Okay. Then acceleration measuring instrument. Acceleration measuring instrument. It is known as accelerometer. Okay. Generally we call this as accelerometer. Now we can write it is an instrument used to measure used to measure the acceleration of a vibrating system vibrating system yeah, if the natural frequency if the natural frequency of an instrument is high compared to that of uh, vibration to be measured vibration to be measure that is we can say omega by omega is less than 1, then we can say that equation equation 7 that we have already derived, which is your Z omega by omega square y divided by 1 minus omega by omega n square whole square, okay, plus 2 zeta omega by omega n square whole root over this equation, okay, can be approximately this one is equation 7, huh? Equation can be approximately simplified as your Z is equal to omega by omega n square y, okay, or you can say it is omega square y divided by omega n square, or we can say it is the ratio of amplitude of acceleration to be measured, amplitude of acceleration to be measured divided by omega n square, the natural frequency. Such instrument, you can write such instrument, such instrument which records the amplitude of acceleration is called accelerometer. Accelerometer. Okay. Now comparing, let's say we give this equation as equation 13, right? Let's say this is equation 13. Now comparing equation 7 and 13, comparing equation 7 and 13, okay, the accuracy, the accuracy of equation 13, or we can say omega by omega less than 1 depends on the validity of expression, validity of expression uh, 1 divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square whole root over is greater than equal to 1 for the value, we can say omega by omega n less than 1. Let's say this is equation 14. Okay. Equation 14. Now in case of accelerometer, this ratio omega by omega n less than 1 implies that the natural frequency, of omega n, which is equal to root over of k by m of the instrument, of the instrument has to be high, has to be high. Okay. This is flex. This condition is possible. We can write this is possible if the spring stiffness, that is your K, is large, and the seismic mass is small. Obviously, if you want a bigger ratio, then K has to be larger and M has to be smaller. Then only the value of omega n will be larger, the natural frequency of the instrument. So and hence we can write, and hence the instrument can be small in size. Then only the instrument can be small in size. Okay. Now velocity pickups. Velocity pickups. Mm, we can write velocity of the vibrating system can be expressed. Velocity of the vibrating system can be expressed mm, from equation 3 that we have already derived. Uh, Displacement small y is equal to capital Y sine omega t, or we can say velocity y dot will be omega y cos omega t. Let's say this is equation 15 phrase for this uh, velocity pickup. Okay. Now the relative velocity can be expressed as can be expressed as uh, z dot representing relative velocity uh, as omega by omega n square, okay, 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square whole root over, okay, cos omega t minus phi, because it is the differentiation of this value, and in the preceding case we have taken sin omega t minus phi, so it will be cos omega t minus phi. So let's say this is equation 16. Yeah. So for a value for your omega by omega n greater than equal to 1, we can write this equation as omega by omega n square 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square whole root over is equal to 1. Let's say this is equation 17. Okay. And the velocity equation, relative velocity equation, z dot is omega y cos omega t minus phi. Okay. So from here we can find out the velocity by using velocity pickups. Let's say this is 18. Now comparing equation 15 and 18, it can be observed that uh, for phase difference, phase difference, for phase difference phi, this z dot relative velocity gives velocity of base uh, as long as equation 17 is satisfied. Okay. And this is possible, and this is possible for large value of omega by omega n. Else velocity of system can be computed from equation 16. What was our equation 16? This equation. Okay. Then we'll proceed further for transducer. Okay. Thank you. So the students will continue with transducers now. Okay. Transducers. A seismic unit that we have discussed in the preceding figure. I can write here. The seismic unit shown earlier measures vibration, which is our input, in terms of the relative motion of its suspended mass, which is our output. For high speed okay, measurement, measurements, it is convenient uh, to convert this output, of relative motion into easily measurable, electrical signals, electrical signal through devices, or you can say device known as transducer. Okay. Now I'll discuss about tachometers. Tachometers, known as your frequency measuring device. Frequency measuring devices. Now uh, we'll discuss about two types of tachometers used. Okay, let me draw the schematic, basic schematic. Let's say this length is your L. Okay. This is called electron tachometer. Okay. And the other category of tachometer is known as Franz speed tachometer. This is called your Franz tachometer. Franz tachometer. Okay. Now this is a single read instrument. Fullerton tachometer is also known as your single uh, read instrument, and this Franz tachometer is a multi read multi-read instrument. Okay. this single reed instrument, this single reed instrument basically uses a variable length cantilever strip. Okay, this is the cantilever strip uh, carrying a mass at one end, whose natural frequency is known as function of length of the strip. Okay. By pressing the clamp end of the strip, okay, if you press the clamped end of the strip against the vibrating body and varying the length of the strip, if you vary the length of this strip uh, against the vibrating body, okay, you will vary the length by means of screw mechanism until resonance occur, frequency can be determined. Okay. In case of this Fram's tachometer, which is a multi-reed instrument, it consists of number of reeds. You can see number of reeds, okay, uh, which are fixed over in the form of cantilevers and carries small masses at their free end. Okay, they carry small mass at the free end. Uh, and the natural frequency of the set of this reed is adjusted to give a definite series of known frequencies. And when this instrument is attached to the body for measuring vibration, the reed whose natural frequency is nearest to the excitation frequency vibrates near a resonant condition and has a large amplitude of vibration. Okay. The frequency of the vibrating body is then given by the known frequency of reed vibrating with maximum amplitude, and the accuracy of the instrument depends upon the difference between the natural frequencies of successive reeds. Okay. The smaller the difference, the more accurate is the instrument, we can say. Okay, so this is all about your tachometer. Okay. Now we'll solve one numerical. Let's say question is given: a seismic instrument, example, a seismic instrument, a seismic instrument is mounted on a machine running at 1000 RPM. The natural frequency of the instrument uh, is 20 radian per second. The instrument records relative amplitude of 0.5 mm. Now question is compute the displacement, velocity and acceleration of the machine neglect the damping of the instrument neglect the damping of the instrument. Now we have the given data. Omega n is given 20 radian per second. Zeta is 0 because damping is neglected. Speed n is 1000 rpm, so we can say omega is 2 pi into 1000 divided by 60, so it is 104.72 radian per second, and the frequency ratio omega by omega n can be calculated as 104.72 divided by 20, so it is 5.23. Now uh, to find out the displacement, let us use this equation. Z by y is equal to omega by omega n square 1 minus omega by omega n square whole square 2 zeta omega by omega n square whole root over. Okay. Now we have Z is given as 0.5, I think, in the question. 0.5 mm, is given. Z is given here. So we have y is equal to 0.5. Okay. Now let us write it this way. Uh, 0.5 divided by y we need, so it is 5.23 square 1 minus 5.23 square whole square plus zeta 0, so this right hand side part will be 0, so if you root over it, so we can instead delete this whole square value, so we have this y as 0.5 into 1 minus 5.23 square divided by uh, divided by 5.23 square, right? So this will give you 0.48 mm. Now the ratio Z by Y is 5.23 square divided by 1 minus 1 minus 5.23 square, okay, which is 1.042. Okay. So this is the displacement. We got displacement, and velocity can be obtained as omega y, so 104.72 into 0.48, that is 50.26 mm per second. Okay. Now coming to acceleration, this will be omega square y, so 104.72 multiplied by 0.48, so this will be 526.81 mm per second square. Okay. So we got the displacement, velocity, and acceleration under the condition that zeta will be kept 0. Okay. Now, likewise, solve one example. Sorry, it is not example. You can take this as an assignment. A seismic instrument has natural frequency of 6 hertz. What is the lowest frequency beyond which the amplitude can be measured within 2% error. Okay. Neglect damping means take zeta value as 0. This is the assignment problem. So further we'll proceed with multi-degree of freedom